Good afternoon and welcome to today's TSP2 Bridge Preservation webinar. My name is Mike Hill and I am the State Heavy Bridge Maintenance Engineer for Arkansas DOT and as well as the current chair of the Southeast Bridge Preservation Partnership. I will be the moderator for today's panel session. The topic of today's webinar is protecting steel bridges from corrosion. Our first speaker is going to be Derrick, who is the Business Development Manager focused on bridges and highways for the Sherwin-Williams Company. He is also a member of the FHWA Bridge Preservation Expert Task Group and has an active member and supporter of the 4 regional bridge preservation partnerships. He is a NACE Level 3 certified. Derrick will present some ideas and technologies for corrosion protection of steel bridges with coatings.
Thank you, Mike. Appreciate it. Thank all of you for attending today. In this first session, I want to talk to you about use of coatings to control corrosion on steel. And with that, while there are many types of coatings that can control corrosion or have been used to control corrosion, the most heavily used is obviously the zinc-rich coatings. And within that, you have inorganic zincs versus organic zincs. And there's can be a fair amount of confusion in the industry about inorganic versus organic zinc. So that's what today's presentation centers on, is looking at inorganic zinc-rich formulations versus organic zinc-rich formulations solely for the use of corrosion control on steel substrates. So just a little overview, briefly give you an overview of the Sherwin-Williams Company at a corporate level or global level. We'll talk a little bit about corrosion and a little bit about formulation, and then we'll dive into qualification and performance of zinc-rich coatings. The Sherwin-Williams Company is obviously a global company. We've been in business for more than 150 years, and we provide services to more than 120 countries throughout our network, and have a network of over 4,700 stores. And we have a dedicated staff of more than 60,000 employees worldwide. As you can see on the screen, our protective and marine market or protective marine division, we have global segments as well as regional segments. And obviously some of the larger segments, the oil and gas, civil infrastructure, water, wastewater, those have more of a global implication and therefore global segments for us. Regionally, we will participate in a number of segments, including the bridge and highway, which regionally we're looking at USCA, the United States and Canada, as a regional segment for the bridge and highways segment of Sherwin-Williams. A little bit about corrosion. Any healthy discussion regarding zinc-rich coatings will be deeply rooted in corrosion theory and corrosion prevention. For this presentation, we're only going to take a brief look at corrosion, as I don't want to wear you out with it. A little bit of corrosion theory and corrosion prevention. Corrosion theory requires 4 basic components be present in order for corrosion to occur. These components are anodes, cathodes, metallic pathway, and an electrolyte. In a corrosion cell, the anode will give itself up or sacrifice itself to protect the cathode, to which it is connected by the metallic pathway and an electrolyte. It's pretty simple to understand that a steel surface is a metallic pathway, and an electrolyte is any solution that will carry a current. Sometimes the more difficult to understand is that within any given steel structure or steel surface, anodes and cathodes already exist. As in the image, when an electrolyte, let's say salt water, comes into contact with an exposed steel surface, the steel surface will begin to rust. The rust spots are the anodes. The non-rusted areas are the cathodes. As the rusting continues and pitting of the surface develops, this is further confirmation that the pitted areas are anodic, as they are giving themselves up to provide a cathodic protection and preserve the surrounding surface. In the bridge market, corrosion prevention typically involves the use of a coating or coating system to control the interaction of the electrolyte from the steel surface. It can be as simple as providing corrosion protection to a steel structure is simply being able to maintain separation of an electrolyte from ever getting in contact with the steel surface. For this purpose, coatings are generally classified as either sacrificial, inhibitive, or barrier based on their pigment. In this presentation, we're going to focus on inorganic and organic zinc-rich coatings as sacrificial primers. Just a little bit about formulation. In very simplistic terms, a coating formulation is comprised of 4 basic components: the pigment, the binder, or the glue, and the solvent and the additives. So pigments provide the functionality, whether it's a primer or an intermediate coat, finish coat, the color and the opacity of the coating, how well it hides. Binders are the glue that form the adhesive and cohesive strength of the cured coating. Solvents allow the components to be dispersed into a homogeneous mixture and evaporate to produce a homogeneous coating. Additives are used to control application attributes such as flow and leveling and produce a uniform coating, as well as aesthetic attributes such as gloss. In looking at inorganic versus organic zinc-rich coatings, we'll focus our attention on the pigment and the binder components. Zinc dust being obviously the primary pigment in the zinc-rich coating. Zinc is quite often used as an anode in the cathodic protection system of steel substrates. In coatings, the quality of the zinc dust is controlled by ASTM D520, standard specification for zinc pigment. Under D520, zinc dust is classified into three types, 1, 2, and 3. This classification separates processed zinc dust based on minimum total zinc content, metallic zinc content, and maximum levels of impurities, most notably lead content. Industry and owner specifications typically establish ASTM D520 Type 2 as the minimum requirements for zinc dust purity. That's primarily to control the impurities or the lead content in the zinc dust. Zinc dust itself is a spherical pigment, and when used in coatings is processed to an average particle size of about 6 microns. This produces a very fine powder that can be uniformly dispersed into a liquid coating. Both inorganic and organic coatings are highly pigmented with zinc dust. The high pigment load is required to achieve consistent zinc particle to zinc particle contact, as well as intimate contact of the zinc particles to the steel surface in order to provide the galvanic protection from the coating to the steel surface. The binder or the glue. The binder, there always seems to be some confusion when you're talking about zinc-rich coatings to an inorganic zinc or an organic zinc. If we start with a simple definition and understand of inorganic and organic, inorganic means non-carbon containing, while organic means carbon containing. Just to be clear, the zinc pigment does not contain carbon and is always an inorganic pigment. The confusion arises in coatings because they are generally classified by their binder type, i.e. acrylics, alkyds, epoxies, urethanes, not their pigment type, zinc-rich. So we talk about zinc-rich coatings, but the reality is when we're talking about inorganic zinc-rich coatings, we're classifying it based on its binder type versus an organic zinc-rich coating. So the subclassifications are inorganic and organic are generally differentiate zinc coatings by their binder, all just to say that an inorganic zinc-rich coating is a highly zinc pigmented coating utilizing typically a silicate binder, and an organic zinc is a highly pigmented zinc pigmented coating utilizing an epoxy binder, possibly a polyurethane binder or other carbon containing binder. Talk a little bit about dry versus cure as we start to move in toward performance characteristics. The terms dry and cure are often used interchangeably in the coatings industry. To be fair, dry typically refers to evaporation of a solvent from an applied film, while cure refers to the chemical process that takes place to produce a solid and durable applied film. The important concept is to understand the curing mechanism to ensure an adequate degree of cure is achieved prior to placing the applied coating into service or top coating. Inorganic zincs cure by hydrolysis. Therefore, the inorganic zinc film requires not only temperature, but also access to moisture, typically in the form of relative humidity, to achieve an adequate degree of cure. Top coating an inorganic zinc with an epoxy intermediate or other highly cross-linked coatings too quickly often leads to a premature coating failure from delamination. Once the IOZ is top coated, it's no longer has access to relative humidity in the air, and therefore the hydrolysis reaction deteriorates to a stop. This leads to undercured IOZs and weakened adhesive and cohesive bond strength, and likely a premature delamination failure. In comparison, organic zincs typically cure by chemical reaction, cross-linking, meaning all the components to achieve proper cure are in the film and only need an adequate temperature to drive the chemical reaction and time. Curing by chemical cross-linking provides very predictable cure schedules and allows for a faster recoat time of the organic zinc, as the organic zinc only needs to release the solvent from the wet film prior to top coating to avoid blistering or pinholing. Even top coated, the organic zinc will continue to cure, provided minimum ambient temperature is sufficient to drive the reaction. Little comparison from a technical application standpoint. There are a few differences between the inorganic zincs and the organic zincs from a technical application. Applying the previous discussion of dry versus cure, IOZs typically dry to handle faster than an organic zinc, but most importantly, the organic zincs are typically cure much faster to recoat than an IOZ or than an organic zinc. And this is displayed on the screen. As I said, there's very few differences. You're looking at it at very similar surface preparation or same surface preparation. The recommended DFTs on an industry basis, your inorganic zincs are typically the 2 to 4 mils versus organic zinc of typically 3 to 5 mils. Your coverage rates aren't substantially different. Dry to handle times are a little bit different. Your top coat times or your recoat times are a significant advantage for the organic zincs. From a practical application standpoint, there are the practical application differences that can substantially impact project schedules and long-term performance. Owners and consultants often specify inorganic zinc primers because they have been the basis of industry standards for performance for many years. But in practice, IOZs are prone to inconsistent cure due to the variations in ambient conditions, as well as in ambient conditions for temperature and relative humidity, as well as application defects such as dry spray and mud cracking. Each of these result in negative impacts to project scheduling and ultimately the potential to negatively impact the long-term performance potential the owner is expecting. Organic zincs tend to provide a predictable cure schedule with a faster recoat time and exhibit greater tolerances for higher film build without detrimental effect to the long-term performance. In short, the organic zincs are easier for your contractors to apply. They are less susceptible to high film build, to issues with high film build. There's been a significant increase in performance characteristics of the organic zincs. Qualifications. Owners and consultants often rely on industry standards to define the basic requirements for both inorganic zincs and organic zincs. One such owner group, NEPCOAT, the New England Protective Coatings Coalition, is made up of the northeastern states from Pennsylvania to Maine. Collectively, these states have developed minimum accelerated weathering performance criteria for coating systems based on IOZs and OZs. The NEPCOAT acceptance criteria and NEPCOAT approved products list are widely recognized and influential across the U.S. In addition to NEPCOAT, the list A's and list B's for the inorganic or organic zincs, there's a number of other industry standards as on the screen. SSPC documents, Paint 20 and Paint 29. AASHTO M300, from a specification review standpoint, we from time to time see AASHTO M300 inappropriately referenced as a requirement for organic zincs. If you're a spec writer setting criteria, AASHTO M300 only pertains to inorganic zincs, whereas SSPC Paint 20 and Paint 29 are both applicable, have sections applicable to inorganics as well as organic zincs. As we look at performance of zinc-rich coating systems, ASTM tests for cyclic weathering, also called corrosion weathering, and salt fog resistance are the primary tests required by performance-based coating specifications. Steel test panels are abrasive blasted, coated, cured, scribed, and placed into cyclic weathering or salt fog test chambers for nominally 5,000 hours of exposure, roughly about 6 months worth of exposure. Cyclic weathering exposes test panels to a salt solution with wet and dry cycles, as well as ultraviolet exposure, while salt fog resistance exposes panels to a separate salt solution in effectively a continuously wet or fog environment. Performance in both tests is predominantly determined by the coating system ability to resist corrosion undercutting, often called creep, at the scribe lines. Undercutting is measured and may be reported in millimeters or in accordance with the rating scale in accordance to ASTM D1640. The coating system's ability to resist field blistering, field rusting, where blistering and rusting are not associated to the scribe lines is also assessed and reported on a 0 to 10 scale, where 10 represents no blistering or no rusting. Common acceptance criteria for scribe undercutting in either test is not to exceed 2 millimeter average undercutting for inorganic zincs based on coating systems, or 4 millimeter average undercutting for organic zinc systems. This acceptance criteria is based historically on accelerated test performances of IOZ and OZ systems from the early to mid 1990s with known acceptable field performances. So as you look at what's on the screen, you see the average. You would anticipate a higher level of performance from the inorganic zincs because they are held to a lower amount of allowable creep, 2 millimeter average, whereas the OZs, organic zincs, are allowed 4 millimeter average. As we'll see, there are formulations. We'll get into some discussion in a minute on formulation on organic zincs that are showing substantial improvement in the ability to meet the standards for inorganic zincs. As we've said that since 2001, the National Transportation Product Evaluation Program, affectionately called NCPP, has been overseeing standardized testing of structural steel coating systems. The performance data reported through NCPP is commonly used by owners to evaluate coating systems for compliance to the performance-based specifications. As previously discussed, many specifications are developed around or influenced by the NCPP code acceptance criteria, which establishes differential performance expectations between inorganic zincs and organic zincs. While these differential performance expectations are rooted in actual test results, the performance capabilities of organic zincs have substantially improved in the last 2 decades. For example, as the graphic illustrates, comparison of NCPP data or NCPP data for a recently evaluated 3-coat inorganic zinc epoxy and urethane system and an organic zinc epoxy urethane system. Current generation of organic zinc formulations are not only capable of meeting the historic performance criteria of inorganic zinc-based systems, they are indeed capable of performing as well as and exceeding the performance of the IOZs. So as you can see on the screen, on the left you have the IOZ epoxy urethane, the tried and true systems of which the vast majority of state specifications or DOT specifications are built around. This particular system performed very well. Cyclic weathering, an average creep of 1.3 with a rating of 10 or no blistering. Salt fog performed at an average of 1.5 millimeters creep, and an adhesion of roughly 2,700 PSI. Now, bear in mind, if you're looking at NCPP data, those adhesion values are quite high typically, and that's primarily because these coating systems are applied in laboratory conditions. There are documents in the industry from SSPC and other entities that would indicate acceptable adhesion values in field applications or general production applications would be around the 400 to 600 psi is a minimum for acceptable adhesion. With any zinc-rich coating, whether it's an inorganic zinc or an organic zinc, you would expect your coating methodology of failure for adhesion testing to be a cohesive failure in the primers, and that's simply related to the high load of zinc dust within each of the binder types. That it makes it prone to cohesive splitting when you're doing adhesion testing. The organic zinc, in this particular instance, the organic zinc epoxy urethane is running less than 1 millimeter average in both tests with a very similar adhesion value. In addition to the innovations in organic zinc technologies and formulations over the past 2 decades, other additional innovative technologies have created options for extremely high performance 2-coat systems that demonstrate their ability to perform just as well as the tried and true industry standard 3-coat systems. The graphic here illustrates a 2-coat IOZ system's ability to perform equal 2-coat organic zinc system's ability to perform equal to an IOZ epoxy urethane system, as well as a 2-coat organic zinc ability to perform, or 2-coat IOZ to perform equal to a 2-coat OZ, and substantially equivalent to an IOZ epoxy urethane traditional 3-coat. The data shows the 2-coat system is available that will provide both time and cost savings for balancing project time and cost savings for the project without detrimental effect on long-term corrosion protection to the asset. in this particular graphic, the inorganic zinc and polysiloxane two-coat system is showing equivalent or performance equal to the three-coat inorganic zinc systems. And the organic zinc two-coat system showing performance that is substantially equal to the bar, to the hurdle set for inorganic zincs at typically at 2 millimeter average, not to exceed 2 millimeter average, a little over on the salt fog, but pretty close. As these are all laboratory tests, the reality is the performance in the field would certainly be negligible. For long-term performance, be negligible difference between a well-formulated, high-performance two-coat organic zinc-rich polysiloxane system versus a traditional three-coat inorganic zinc, and there's quite a bit of value to be gained in the two-coat options. In summary, the current organic zinc technologies meet traditional inorganic zinc performance expectations and provide value-added cost savings and flexibility without compromising long-term corrosion protection of high-valued structural steel assets. A quick summary, many of the inorganic zinc products on the market are three-component inorganic zinc, meaning you have a binder, an accelerator, and a dust. The organics, many of them are epoxy, so you have a component A and a component B, the epoxide and the amine, and then a dust. Your coverage rates are substantial, there's not a lot of difference in coverage rates. Again, we talked about handle and top coat times or recoating times. There's a significant advantage to the organic zincs. And performance, in the grand scheme of things, there is very little, if any, performance differential between the well-formulated organic zinc-rich primer and an inorganic zinc-rich primer under the current formulations, current timeline. So with that, I'd like to say thank you, and I look forward to your questions at the end of the presentations.
I am so happy. First of all, I have to say thank you for allowing me to be here. I'm very, very excited to be here, and I can't wait to kind of show you what we have done as a local agency. I have to say that Travis stole a lot of my thunder, so maybe it'll be a repeat, but again, maybe if it's a repeat, that way we'll kind of get the point, right? I want to go and talk to you a little bit today about what we at Harrison County have done as far as a bridge preservation program. Now, the first thing that I can tell you is that one of the things for us is that, I don't know about any of the other locals, but a lot of times for us, you know, we don't like that word change. Sometimes I think that's more of a four-letter word than the letters that it actually has.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.